When you're working with quantitative data in an extensive research design, you've got to understand how to manage and analyze that quantitative data. And so in this video, we're going to talk a little bit about some key things you need to know about statistics heading into the research design process. In this video, we're going to talk a little bit about two branches of statistics that you might be working with when you're doing research. One is called descriptive statistics, and the other one is called inferential statistics. And they both have different characteristics. They have some similarities, but they also have some differences in terms of what kind of expectations we have with how to work with them and what kind of work they can do for you. If you're using statistics or quantitative data in a research project, what are the pros and cons of it? Or what are the strengths of this kind of analytical method? Well, the biggest strength of quantitative methods or statistical analysis is that it's really good at finding patterns, and it's really good at summarizing data, or taking a big complex data set and taking it down to a level that's just easier to digest. So that's what statistics, quantitative data sets are really good at doing. The disadvantage, or maybe some of the weaknesses of quantitative analysis, although it is easy to provide a lot of statistics about something, or it often can be easy to just throw out and just put down a lot of stats about the topic that you're studying. Sometimes those statistics might reveal patterns, but they might not address the question that you're trying to answer if you're trying to really understand underlying processes. So statistics and looking at variables and those sorts of methods for analysis are not often, or not sometimes, the best at trying to understand really how or why something is happening out there in the world. And so for that, we use statistics usually in an extensive research design approach, and we might use a different sort of analytical method for an intensive research design approach, or in other words, for a case study. And before we continue, just know that you can actually use statistics and you can use quantitative data in both an extensive and intensive research design types of projects. And this can be of course, this is in physical geography, where most of the data is quantitative in the first place, but also in human geography and GIS. You can use statistics in both extensive and intensive research design. The big difference between how to make full use of the strength of quantitative analysis for an extensive research design versus how it might fit better into an intensive research design, we find that in the distinction between descriptive and inferential statistics. So let's talk about that for a second. So descriptive statistics is where we use those terms that you're probably already familiar with, like an average or a percent. These are called descriptive statistics. So for example, if you calculated the average time that students spend walking across campus, or the average amount of time it takes to walk from the parking lot to the classroom, right? That's an average. That falls under what we call descriptive statistics. If you wanted to find out the percentage of students who walk to campus, drive to campus, or take the bus to campus, right? These would all be descriptive statistics. Another term that you might be already familiar with, and you should become familiar if you're not already, is standard deviation. And this is a very important thing. And, we do use standard deviation in a lot of our more advanced, sophisticated quantitative analysis as we get into inferential statistics. But it is also a measure of descriptive statistics. So what does that mean, descriptive? It just means literally that you're describing a data set, or you're describing really what your sample is. So really, a descriptive statistics is taking your sample that you have for your project and just describing the quantitative characteristics of that data set. So here's an example from a project that I worked on before, in which community gardeners were asked about the types of challenges or the types of issues that they faced most often, or the ones that were most significant, like the biggest issues that they faced. And So people talked about funding, people talked about just the people side of things, getting people to be there in the garden doing the work. They talked about access to land, losing access to land, finding new sites, and also about things like materials that you use in the garden, just like getting access to soil, compost, consistent water supply. All right. And then you just have the percent of respondents, right? The percent of people from the project who's mentioned that thing, right? 61% mentioned funding was the biggest problem that they faced. So this is not a really sophisticated form of statistics. This is just descriptive statistics. So it's the simplest kind of stats, but it can usually be really important because before you do those really sophisticated, advanced kind of quantitative methods, we usually do want to just get a baseline understanding of what it is that we're dealing with. So this kind of descriptive statistics, we can use those in both an extensive or an intensive research design kind of projects. Now, if you're an extensive research design and you're really trying to understand, are there really any patterns here, then you usually have to go one further step and go into inferential statistics, which we'll get to in a second. And if you're doing an intensive research design, then often we can use a lot of descriptive statistics, and then we might combine that with some other methods to explore more of those processes rather than looking for a statistically representative pattern in the data set. When you move into inferential statistics, this is when we get into some of the more advanced or sophisticated analytical techniques. And here you will find some terms that you might know, or if you don't know, things like independent variable and dependent variable. So when you hear those kinds of terms being used, you know that this is inferential statistics. All right, so what does that word mean? So it means that you're trying to infer something. So infer means that you have your sample, you have your data set that you have collected. And of course, if you remember from our sampling lessons, sampling means that you can't research or you can't collect data on everything in that population, right? You can't study every single river or every single neighborhood, right? You have to take a sample. And so when we do inferential statistics, we're trying to find out how well does what our sample says, how well does that say something about that entire population? And so we have to apply a few different rules, and it has different expectations. And so when we talk about independent and dependent variables, that's the idea that if an independent variable, if that changes in value, like if income goes up or down, or if water flow in a river increases or decreases, then does that affect another variable? And that would be your dependent variable. So a dependent variable in the rules of inferential statistics, an independent variable would cause changes to the value of a dependent variable. Or in other words, the value of a dependent variable depends on what the independent variable is. And that really is at the core of quantitative methods, and especially extensive research design, where you're trying to find if a pattern exists between certain variables. We always have to keep in mind, however, that we have intensive research design to really explore the underlying reasons for that. So just always be on your toes that in statistics, we use the word causation, right, to say that an independent variable, does it cause the dependent variable to change in value? So in statistical language, there's that word cause or causation. But we also have to know that there's a more deeper meaning of the word cause, that if we can use all of the statistics in the world, that would really confidently tell us that one variable is tightly linked to changes in another variable, but that these statistics don't tell us really why that is, right? What's really driving that thing that's happening there. So for understanding those more deeper underlying processes, that's what intensive research design is for. But right now we're talking about statistics, so let's continue with that. So how do you know if two variables are really linked to each other, right, through that independent and dependent relationship? Well, we use some of our other terms in stats that you should be familiar with, such as correlations, regressions. All right, those are two of our more important things. Of course, correlation isn't usually used as the biggest one. That might be a first. That's one part of doing some statistical analysis. But really, regression is the more of the standard. That's the kind of thing that you would look for, is something called a regression. We can use a lot of other techniques out there, such as t-test. So if you wanted to compare the average or two sets of averages against each other, for example, if you found out what the average commute time is for CSUN students, and then you wanted to compare that to the average commute times of other universities in Southern California, well, you could do what's called a t-test. And t-tests are used to compare averages to find out, are they pretty much the same thing or are they different from each other? All right, so this is the kind of thing that you would learn in a quantitative analysis course, which in our program is Geography 460. All right, so if you're either a physical or human geographer or a GI science major, and you think you're going to need to get some skills with quantitative analysis, you really need to take that course. We use inferential statistics to get a connection between our sample and a bigger population, right? Whether that's trying to make an inference between the sample and a population, whether we're trying to understand a relationship between a dependent and an independent variable, or whether we're trying to compare two different samples against each other. We can also use it in more of a spatial sense in GIS, and a lot of our spatial statistics tools in GIS utilize inferential statistics. And if you open up any of these tools in your GIS software and open up the help function for these, you can usually see sometimes they can be pretty complex equations of how these things are put together. So for example, you might want to know if eagle nests are randomly distributed across a forest or if they actually tend to be clustered together, right? There are certain spatial statistics formulas that we need to apply, and we would need to have a large enough sample. So remember, that's one of the other things with extensive research design, is we have to have a large enough sample for this to be a good answer. And with our GIS tests, with our GIS tools, often the tool will tell you, what's the minimum sample size you need for that. Here's an example of what descriptive versus inferential statistics would look like in GIS, for example. So you've got here on the left side a map of, this is the city of Trenton, New Jersey, and these are neighborhoods in the city. And each neighborhood is symbolized according to the percent of parcels in that neighborhood that are vacant. Okay, so that's just we take each neighborhood and then look at what's the percentage of the parcels or the percentage of the properties in that neighborhood that happens to be vacant. And we can look at that map and we can start to see some kind of spatial patterns there. But this is descriptive in the sense of we're just describing the data set. We're not applying any of our advanced statistical tools to really get a good idea of, can we confidently say that certain parts of this city are more vacant than others. So for that, we use some tools such as the hotspot analysis. And so this is in some of our GIS software, it might just be called informally the hotspot analysis, but it does have a more formal name, such as the Geddes or GI star test. And in that one, you see that we have areas of red and we have areas of blue. So in this test, it takes each neighborhood and it compares each neighborhood to all of the neighborhoods that are around it to see, is there a pattern going on that really differs? Is that neighborhood really significantly different than the other neighborhoods that are around it? So there's an example of descriptive versus inferential that you can see in a GIS example. All right, let's move on to some of our basic concepts in quantitative data that everybody needs to know. And this includes just what are the types of quantitative variables out there. And we've got nominal, ordinal, and interval ratio scale data. Okay, so nominal, this is descriptive. This is descriptive data. So this is just telling us about something. It's just like an attribute, like the type of soil or the name of a city. And this is important because nominal data can have a number to it. So soil type, you could have clay soils is assigned a number 1, sandy soils is assigned a number 2, and silty soils is assigned a number 3. All right. Now, these have numerical values, but that doesn't really make them quantitative data in the same way as something that has a measured value, right? The number one there doesn't mean that you've measured one of something, right? It just means that you've assigned a category. That's really important to know, because just because there's a number to it doesn't make it truly quantitative data that you can crunch the numbers, right? We can do other stuff with it, but we can't analyze it in the way that you could analyze, the amount of nitrogen in the soil, for example. Okay, ordinal data, that is the type of data that implies an order to the data. So ranking from high to low, right? So 1, 2, and 3 would mean like highest risk, 2, medium risk, 3, lowest risk of wildfires, for example, for a land cover pattern. And then our last category that we're going to talk about is sometimes it's called interval, sometimes it's called ratio, scale. There's some minor differences here, but basically this just means something that you can actually measure a quantity of, right? So this is just an absolute number, right? So an area or length, height, quantity, temperature, right? So just an amount of something. This is when you actually measure things. And so that last one is something where we can apply some of our mathematical formulas. These are important to know just because you don't want to mistakenly use a math equation on a nominal data set, because then you would just kick nonsense numbers out of it. And if you've got that kind of data and you wanted to apply a clustering or a hotspot analysis to the soil types, we might need to make some changes to that data set. And these are the kinds of things, of course, that you learn in some of your other methods courses. Some other basic things that we all need to know is just, what is an average? So we need to know that an average also is the same thing as the mean. And that just means you add all the values in a data set and you divide by the number of observations. So the average grade on the test in your class would be what each student's grade is. And then you find the total of all of those grades. And then you divide by the number of students in the class. And then you get your average score. One of the problems or one of the challenges with working with averages or the mean is that if you have an outlier, so an outlier is another statistical term that we need to know, is that in our distribution of our values, if there's any really high or really low values, then that can really throw off the average value. So in another lesson, I've talked about how, imagine if somebody in class won the lottery and then they walked into class that day, the average income of the class would suddenly skyrocket and be really high. Even though it's just one person whose income has really drastically increased that much. So outliers can really drastically alter the mean, or they can skew, right? So this is another word, is skew. How do we account for this? So median is another term that we use when we're looking at our data sets. Okay, when we're working with quantitative data, usually we're often just looking at these descriptive statistics to get an idea of what our data set's trying to tell us. So the median is just the value that's in the middle. So if we're looking at income, if you had 20 students in the class, then we would organize the student income from lowest to highest, and then we would just count off, the 10th student. All right, the 10th highest income student, what is their income? And then that would be the median. So to find the median, you sort values in a data set from low to high according to whatever the variable is that you're interested in, and then you find the value that's right in the middle. Another example here, just real easy, is in this example data set, we've got a few figures here, 520, 520, 580, 580, and 9,000. The average value of all those is 2,240. But of course, 2,240 does not give us a really good picture of what that data set really is all about, right? Most of those figures are in the 500s. So the median would just be that middle value. Line up all of those all of the values from lowest to highest, and which one is in the middle, that's your median. So median, mean, these are two of our most frequently used descriptive types of data. And then, mode is another one. We don't see it being used that often, but mode is just the most frequently observed value in a data set. The last one that you should know about descriptive statistics, and this one is really important when we get into inferential statistics, is something called standard deviation. And so standard deviation is a measure of variation. So this means how much do the values in a data set vary outside of the average value. So one way of talking about standard deviation is, let's go back to a class example, right, of our test grades, right, or grades on a test. Let's say that you have the average value of the average score on a test was a C. Okay. Does that really tell you how well everybody in the class did? Well, we can look at another value called standard deviation to find out more about that data set. So if we see that the average is a C, but then the standard deviation is 20 points, that would mean that the scores are not just based around that C grade, but also there you've got a good amount of grades that are up around 90, right? Maybe up in the 90s. And then you've got some grades that are down in the Fs and Ds, right? So you've got that distribution will be flatter. All right. If the average grade was a C and the standard deviation was 3 points, that means that pretty much everybody in the class got a C on that test. So a standard deviation is a really useful statistic to use. And in the world of statistics, we can look at graphs like this. And if we see this is what we would call a normal statistical distribution, or that bell curve. And we have some statistical kind of laws or understandings that would tell us that one standard deviation above and below the average value, if it's a normal distribution, is going to hold 68% of all the pieces of that data set. So again, let's say like our test score, right? Whatever that average test score is, if our scores are normally distributed, that would mean 68% of the students in the class got within this range. Maybe you got a couple students that did really great, maybe a student who did really poorly, but most of those students are going to be within one standard deviation. So one way to read standard deviation is it's always a plus and a minus, right? It's like you've got your average value, and then one standard deviation is one of that number above the mean, and then one of that number below the mean. So it'll be like negative that value and then positive that value. So these are things that you would learn much more in depth in a quantitative methods course such as Geography 460. And we need to understand how to apply them to our research design process, that we need to link these to the right kind of research question. Remember, if we're doing inferential statistics, we're looking for patterns. We're trying to find out, do patterns exist? So going back to this example of the vacant properties analysis, our inferential statistics here showed us we have a pretty good idea that there are vacant properties clustered in this part of the city. The blue areas, those are cold spots. Those are where there's actually a big cluster of occupied properties. Okay, so that's really useful. And something else there, just as a bonus, is you'll see that it says 99% confidence, 95% confidence, and then in the middle, there's not significant. So that's another giveaway that this is inferential statistics, is that one of the things with that kind of statistics is you're essentially trying to make a guess to say, how confident are you that that neighborhood is a cluster of vacant properties? Well, the formula, right, the equation, the way the math is working out, it's saying that we can be 99% confident that that neighborhood is a cluster or a hotspot of vacant properties. Okay, so that's great, right? We have a good understanding of a pattern there, but it doesn't tell us why that vacancies happen or why those occupancies happen. It doesn't tell us about those underlying reasons, right? So it doesn't tell us, why did people have to move out? Was there illegal evictions going on? What kind of processes driving poverty, driving housing development? What kind of legal processes were going on? What kind of economic processes are happening in the city going back for decades related to deindustrialization of factories leaving and moving somewhere else, right? These are much more deeper and more complex processes that are examined through an intensive research design project. We can look at those other variables, certainly through extensive research design. We can look at those variables through statistics, but really getting a really good and honest understanding of those underlying processes is going to be more difficult through quantitative methods, which on the other hand, quantitative methods are really great at looking for patterns. So we need, right, both kinds of knowledge are very important. And as geographers, I hope that we understand that both types of approaches, intensive and extensive, are quite important.